Alright, so hopefully you watched the animation video before you're watching this one. If not, I would suggest that you go back and watch that animation of the derivative and how we come up with it. Hopefully make a little more sense as we look at the slope of the secant line and slope of the tangent line algebraically in this video. So if you remember from that video, we were given a point P, and that point P correlated to an x value. We can also get a y value out of that. So we can get x and f of x. So I got my x value and my y value for point P. Then what I did was I wanted to come over here to get my x plus h. And that gave me my point Q. And that also gives me the coordinates of that point, x plus h and f of x plus h. And remember what we wanted to do, well, what we did, we created a secant line. And what we wanted to do was to get this point P to move along the graph here and to make it to point P. And we did that by taking h and making it smaller and smaller and smaller. Well, before we do that, we can find the slope of the secant line. So the slope of the secant line is also called the average rate of change. And hopefully we remember that from Algebra 1. So how do we find the average rate of change or the slope of that secant line? Well, we can do it in a lot of different ways. We can do delta y over delta x, change in y over the change in x. We did rise over run. We did y2 minus y1 over x2 minus x1. So all those are things that we did to find the average rate of change. So I have these 2 points. I'm going to go ahead and find the slope between these 2 points. So I take my y2, my second y value, which is the f of x plus h. From that I'm going to subtract my first y value, which is f of x. I'm going to divide that by the x plus h, or the x value of my second point, minus the x value of my first point. Cleaning this up, we have f of x plus h minus f of x all over h. Oh, do we remember this? How many times, how many conversations, where and why will I ever use this? Well, here we are. So we now have the slope of the secant line. How can I come up with the slope of the tangent line? Remember, the slope of the tangent line from the video is going to be this line right here. So how do I get this secant line to become the tangent line? Well, I can do that by taking this x plus h, or this point Q, I guess, and moving it along that line, which takes this x plus h and moves it closer to x. And we're going to take h, and we want h to be continuously smaller. So h is going to get closer and closer and closer to 0. So we're going to take the limit as h approaches 0 of f of x plus h minus f of x all over h. And this is the slope of the tangent line. We also call this the instantaneous rate of change. We also are going to find that this is going to be called the derivative. So anytime we're asking you to find the slope of the tangent line, find the instantaneous rate of change, find the derivative, this is what we're looking for. We're going to denote this as f prime of x. So it's going to be f, it's going to be a little dash or a little line, and then our parentheses of x. And that's what we're going to be looking for. So let's go ahead and look at a couple of examples of how this is done. So here's our f of x, 3x minus 1. We're looking for f prime of x. So by definition, we're looking for the limit as h goes to 0 of f of x plus h minus f of x all over h. We've had a lot of practice finding that. So we can go ahead and find that. We can find f of x plus h. F of x plus h, we take our x plus h, plug it in for our x's. we get 3 times x plus h minus 1. I'm going to come down here and write that. From that, we're going to subtract f of x. Well, f of x is simply replacing your x's with x, we get 3x minus 1. So we're going to subtract off of this 3x minus 1, and we're going to divide that by h, and we're going to take the limit as h approaches 0. We can clean this up just like we have done in the past. We have 3x plus 3h, when we multiply that out, minus 1, multiply the negative through, we get minus 3x plus 1. Anything without an h is going to cancel. So we're going to see this 3x is going to cancel, this negative 1, positive 1 is going to cancel. So we're left with 3h over h. So we're taking the limit as h approaches 0 of 3h over h. If I were to plug in the h or 0 in for h, I'd end up with something that's undefined. However, we can simplify this by canceling out the h's, reducing the h's. So now I'm looking at the limit as h approaches 0, of 3, which is 3. So that is f prime of x. That is the instantaneous rate of change, or the slope of the tangent line. So the slope of the tangent line is always 3. Well, if you think about it, f of x equals 3x plus 8, or 3x plus minus 1, is a linear function. It should go through negative 1 there. And the slope of that is 3. So at any given point in time, we know the instantaneous rate of change is going to be 3, because we're always coming up 3 over 1, up 3 over 1. That isn't always the case. It's not always constant, as in example 2, where we have 1 over x. Here, if I take the limit as h approaches 0 of f of x plus h, that's going to be 1 over x plus h. From that, I'm going to subtract my f of x, which is 1 over x, divided by h. Now I'm going to go ahead and simplify this. I'm going to find a common denominator for the numerator there. So I get x minus x plus h. My common denominator was x times x plus h all over h. Hopefully I didn't go through that too fast. My common denominator was the two of them together. This term over here needs an x in order for it to look like x times x plus h. This one here needs an x plus h to make it look like x times x plus h. Distribute your negative through, so we get x minus h. So we're looking at the limit as h approaches 0 of negative h over x times x plus h times, take this h, multiply by the reciprocal of 1 over h, so the h's are going to cancel. We're looking at the limit now of h going to 0 of negative 1 over x times x plus h. Remember our rule for limits, we're taking that 0, plugging in for h's, so we get negative 1 over, well, that goes to 0, we have x times x, we get x squared. So notice here, we get an algebraic, or a variable in our derivative. This is our, again, f prime of x. Always want to label our derivatives with f prime, so we know that it's f prime and not f or something else. So notice this now, the derivative or the slope of the tangent line depends on what the value of x is. So it's ever going to change. And if you think about it, the graph of 1 over x is going to look something like this, another parent function. So at anywhere on this graph, we should see that the slopes are going to be different. So up here, we have a very steep negative slope, if you wish, to where over here, it's very flat. So those two slopes of the tangent lines are going to be very, very, very different. So depending on what the x value is. Think about plugging some values in. And that's what we're going to start doing later on. So if I find the derivative when x equals, let's say, 3, that gives us a slope of negative 1/9. Whereas if I give you the slope, or ask you for the slope when x equals 4, then we're going to get a value of negative 1/16. So notice we get two different values. Up here in this example, it was constant. Up here, it was constant. It was always 3. Didn't matter what the x value was. Down here, we see it's going to vary. So what can we do with this, and what are we going to ask you to do with this? Well, we're going to ask you to find now the value or the slope of the tangent line or the instantaneous rate of change when x equals 3 of this function. So again, we're always going to start out the same, limit as h goes to 0. I'll go ahead and write that out again, f of x plus h minus f of x all over h. Very important that we remember this formula because we're going to use it and use it and use it again. So we're going to look at the limit as h goes to 0. We have our x plus h squared plus 1. From that, we're going to subtract x squared plus 1 all over h. Multiplying this out, that gives us x squared plus 2xh plus h squared. Multiply your negative through. So cleaning this up just a little bit, we have x squared plus 2xh plus h squared minus x squared minus 1. Do not forget to multiply that negative through. Cancel out your x. Oh, I lost my 1, didn't I? We have a 1 in there somewhere. There. Oh, my plus 1 there. So our x squareds are going to cancel. Our 1s are going to cancel. Remember, anything without an h should cancel. That's why I thought, hey, I don't have a 1 to cancel there. So got to go back and look to see where it is, how it happened that I missed it. So I can factor out an h now of what's left over. I have 2x plus h in the top, in the numerator, divided by h. My h's will now cancel. So now I have my function, limit as h goes to 0 of 2x plus h. So my derivative as h goes to 0, we replace that with 0, we end up with 2x. That's my overall derivative. That allows me to find the slope of the tangent line when x equals 3. So 2 times 3 gives me 6. And that's the slope of the tangent line or the instantaneous rate of change of this function when x equals 3. Other things that we can do with this, we can find the equation of the tangent line. Given the function f of x equals x squared minus 3 when x equals 1. Well, what do we need to be able to find the equation of the tangent line? Well, to find an equation, we need a point, and we need the slope. Well, if I have an x value, that gives me part of my point. I also need my y value. Well, how do I find my y value? Well, if I know that x equals 1, f of x equals x squared minus 3. Remember, that's also y equals. So I can take my 1, plug it in there, and I get the point of negative 1, negative 2. How do I find the slope of the tangent line? To find the slope of that, I need to find the derivative. So I'm looking for f prime of x. Remember that f prime of x is the limit as h goes to 0 of f of x plus h minus f of x. You're going to get tired of listening to it, but I'm going to say it anyway, divided by h. So I'm going to plug my x plus h in. Some of you are going to get very good at putting this together very quickly. Others of you, it will take a little bit of time. Please take the time. Make sure you understand this process. It's not going away for us for a while. There are some shortcuts to this. However, we won't learn those until the next section. And we need to be able to recognize this as we get into our problems later on. So now we can go ahead and cancel our x squareds, our 3's. So we have h, factoring that out, 2x plus h over h. The h's are going to cancel again. We're taking the limit as h goes to 0. So that's going to give us the derivative of f of x equals 2x. Remember, h went to 0. I want to know when x equals 1. So I'm looking for f prime of 1. That gives me 2. So now I've got my slope is going to equal 2. Now I can go and write the equation of the line. Remember, the equation of a line is y minus y1 equals m times x minus x1. So we have y minus a negative 2, so y plus 2. That's going to equal our slope, which is 2, and then x minus 1. And that's going to allow us to come up with the equation of that tangent line. No need to manipulate this, but if you want, you can solve for y. What y would equal, multiplying your 2 through, we get 2x minus 2 minus another 2 gives us 4, if you wish. The last thing I want to do is to talk about sketching the graph of f prime given f of x. So when we talk about the graph of f prime given f of x, we're looking for the slope. So what is the slope of this graph? Well, here the slope is going to be negative 1 all the way here until 0. So we're going to have negative 1 all the way here until we get to this point here at 1. When we get to this point, it switches to being 1. So that's going to be the graph of f prime of x. That hopefully looks a little bit familiar to you from your note cards as we did last year. All right, and then f of x here. So here, notice we have a couple of things happening. We don't really know what all these slopes are. They're not constant. These aren't constant, and these aren't constant. But we have an idea of what's happening. We know that we have a positive slope. We have positive tangent lines that we can draw into here until we reach this point here. Here we have a horizontal tangent line. So we know that from negative infinity all the way here to negative 3, it's going to be a positive slope. And then we hit 0. We can graph 0. So here at negative 3, we're going to have 0. We know we're going to have a positive slope. We don't know what it's going to be, but we know it's going to be a positive slope. So it's going to be up in this region somewhere. From negative 3 to 2, we have negative slopes. So it's going to be below down here. And then at 2, again, we have another horizontal tangent line. So that slope is going to be 0. And then we're going to, again, have positive slopes. So it's going to be above here. So we're going to have positive slopes of some sort. Notice they're going to start very steep, so they're going to be very high. So that number is very high. And it's going to get closer and closer and closer to 0. Now we're going to go negative. And then we're going to come up to this point, and we're going to become positive. Now some of you are asking, well, how do I know this is going to happen in here? Well, we'll get to that point. There's going to be a point, it's about right in here. We call this the point of inflection. The point of inflection is where our concavity is changing. Way down the road, that's what's going to happen. Again, if we have a positive here and a positive here and negative down here, we know that these are going to all be continuous through here. So we're going to be able to draw that graph. Hopefully that makes a little bit of sense. If not, send me your questions. Good luck.